Hi everyone! In today's video, we're going to be going over the graphical analysis of kinematics. So, we're all familiar with slope if we have taken pre-algebra, and we know that a basic linear equation is in the form of y equals mx plus b, where m is our slope and b is our y-intercept. So before we go any further, let's take a look at our basic concepts of displacement, velocity, and acceleration. Let's look at the units of each concept. So we know that displacement is delta x, and we know that velocity is delta x over t. We also know that acceleration is delta x over t squared. And by the way, this t is delta t, by the way. So what I'm noticing here is that velocity is also displacement divided by change in time, and acceleration is velocity divided by change in time. So if we had a graph where the y-axis was displacement and our x-axis was time, the slope of that graph would give us velocity because it would be rise, which is displacement, over run, which is time. And if we had a graph where the y-axis was velocity and the x-axis was time, then our slope would give us acceleration. Okay, so let's look at the graph we have here. So easily, looking at time equals 3, we want to know our displacement and our velocity. So with our graph, we can go to the time equals 3, go up, and we see that our displacement is 3 meters. So we can say that our displacement at time equals 3 is 3 meters. So what about the velocity at time equals 3? Since we know that velocity is displacement over time, and our y-axis is displacement and our x-axis is time, we simply take the slope at time equals 3. So if our graph was curved, we would use calculus to figure out the derivative of our graph at time equals 3. But since our graph is linear from 0 to 5, and then another piece of linear from 5 to 10, and so on, we can simply take the slope of our graph from 0 to 5, which would give us a rise of 1, 2, 3, 4, 5. So it would be rise over a run of 1, 2, 3, 4, 5, which would mean our velocity is 1 meter per second because our units are meters divided by seconds. So now let's take a look at our displacement when our time is 7 seconds. So simply we go to the 7 seconds and then we go up and we see that our displacement is 5 meters. So our displacement at time equals 7 seconds is 5 meters. And now we have to find the velocity. Same thing, this time we take the slope from the piece of 5 to 10 because those two have the same slope. We can see that our rise is 0 and our run is 5, which gives us a slope of 0. This tells us that our velocity is actually 0 meters per second, which means between times 5 and 10, or simply exactly at time 7, our object is not moving. So now that we know how to find the velocity from a displacement time graph at a certain time, how can we convert this entire graph of the displacement of an object to the velocity of that object during its entire time period? So once again, we know that if we have a displacement versus time graph, the slope of it can give us the velocity. Because our graph isn't curved, we don't have to use calculus or take the derivative of our graph to figure out the velocity. A derivative is just a slope at every single point. Here, we have a linear line that stays linear from 0 to 5, and then changes its slope from 5 to 10 seconds, and then once again changes slope from 10 to 12.5 seconds. So for each of these intervals, we can find the slope because it's simply a linear graph. Okay, so from 0 to 5 seconds, it looks like our rise is 5 meters and our run is 5 seconds. So our velocity would be 1 meter per second from 0 to 5 seconds, like so. We would start here and continue on until 5 seconds. And then after 5 seconds, we notice a change in slope. We have a flat graph right here, which indicates that our slope is 0, or our velocity is going to be 0 from 5 to 10 seconds. Like so. And then, let's calculate our slope from 10 to 12.5 seconds. Since 12.5 isn't a really nice number, let's use this point and this point here because they are whole numbers and they land right on a point. So our rise is down 2, which means -2, and our run is 1. So this looks like that it's -2 over 1, and so our slope is going to be, or our velocity is going to be -2 meters per second from 10 to 12.5. So right here, -2 meters per second from 10 to 12.5. So this is our velocity versus time graph for the same motion of the same object's displacement versus time graph. Okay, now what if we had a velocity graph of our object and we wanted to figure out the acceleration? So, same thing, we would do the slope at every point, and once again, because our graph is linear, we don't have to use derivatives or calculus to figure this out. So let's break it up into segments, 1 to 2, and 2 to 5, and then 5 to 7. So the slope from 1 to 2, our rise is 40, and our run is 2. So this gives us a acceleration of 20 meters per second squared. And because my graph here doesn't have it, I'm just going to say that that's 20. And that's going to last from 0 to 2 seconds. So 0 to 2 seconds, we have an acceleration of 20 meters squared. From 2 to 5, our graph is horizontal. This tells us that the slope is 0, or the acceleration during that time period is 0 meters per second squared. So from 2 to 5, 0 meters per second squared. And then our interval from 5 to 7. Our rise is once again 40, and our run is 2. So that's going to be 20, but negative because our rise is downwards. So let's assume again this is -20, and that's going to be from 5 to 7. So here. So this is our acceleration graph for this particular velocity graph. Okay, so now we know how to go to use slope to find either the velocity or acceleration of a graph. But how can we use a velocity graph or an acceleration graph, which we will go over later, to find the displacement of our object? So before we go into any formulas, let's take a look at our units. So we know that velocity is meters per second, or displacement over change in time. And our displacement is just our delta x. So what we have to do is multiply velocity by time to get to displacement. So if our graph is velocity versus time, and we have to multiply our velocity by time, we have to essentially find the area under our graph to find the displacement. In calculus, finding the area under a graph is called taking the integral of the graph. In this case, since our graph is linear, all we have to do is break it up into triangles and rectangles. And for each point in time, we have to take the area from 0 to that point. So from 0 to 1, we find the area, which is going to give us at time 1 second. Our displacement is going to be 1 times 2, which is 2 divided by 2, and that's going to give us 1 meter. So at 1 second, our displacement is 1 meter. Let's keep going. Okay, so now let's look at time 2 seconds. Remember that we're supposed to find this entire area right here. So it's base times height, so it's 2 times 4, which is 8. And it's a triangle, so divide by 2 is going to give us 4. So this tells us at time 2 seconds, we have a displacement of 4 meters. So now finding the area under the graph at time equals 3 seconds. We know from 1 to 2 it was 4, and then a rectangle from 2 to 3 is going to be 1 times 4, and 4 plus 4 is 8. So our total area from 0 to 3 is going to be 8, which tells us that at 3 seconds our displacement is 8 meters. So right there. Okay, I went ahead and did the rest of the times, and this is the data points on our displacement graph. So let's draw a line through it and see kind of what this shape is going to give us. So from 0 to about, I think, 2, it looks a bit curved, and then it gets pretty linear, and then it starts curving back down again. And let me use white there because I ran out of space on my graph. So there's something pretty important that this graph tells us about the velocity graph again. So remember that displacement, the slope of our displacement graph is going to give us the velocity graph. And the slope of a velocity graph is going to give us the acceleration graph. So before, the slopes of our displacement graph were all linear, which gave us horizontal velocity graphs. But this time, our displacement graph, our velocity graph, the lines of our velocity graph are linear. And so this gives us a curved displacement graph. So right here where velocity is linear, we have a bit of a curved velocity a curved displacement up to 2 seconds. And then when our velocity is flat or 0 again, we have a linear section. And then right here, when our velocity is a decreasing linear, we have something that's curving down. And this goes back to the concept of calculus, where some of you may or may not be familiar with. So the derivative of our graph tells us the change of our graph. So in the beginning from 0 to 2 seconds, we see an increasing change. And the increasing change tells us a slope that is linear, which is our velocity graph right here. And then after 2 seconds, we notice linear, or we notice a consistent change, which is going to give us this horizontal velocity. Notice that our velocity is not 0, it's 4 meters per second, but it's consistent. That's why we have linear from 2 to 5 seconds. And then after 5 seconds, we have a curve down. So the change of our graph is a slope downward, telling us the slope is going to be linear down, which is shown in our velocity graph. So as you can see, the area under our velocity graph can give us the displacement. And the slope of our displacement graph can give us our velocity. Now let's try this with acceleration graphs. Okay, so now let's do the area under acceleration to figure out velocity. So for 1 second, we have an area of 4, telling us that for 0 to 1 seconds, we have 4. And then from 0 to 2 seconds, which is going to be this, that's going to give us a velocity of 8 at 2 seconds. And then continuing the pattern, this is going to be 12. And then this is going to be 16, which is going to be kind of up there. So it looks like that our graph is going to be linear, and we don't need to find the rest of the area to figure this out. So this looks like a linear graph, and this tells us that if we have a horizontal line, finding the area under it is going to give us a linear graph. And if we have a linear graph, finding the slope of it is going to give us a linear line. So let's further look at some relationships between these 3 graphs, acceleration, velocity, and displacement, without having to calculate. Okay, so now let's look at the relationships between acceleration, velocity, and displacement for a single scenario without having to calculate. Okay, so we know that acceleration is caused by a force. So in Physics 1, or AP Physics 1 and 2, our acceleration is going to be uniform, which means that for all times it's going to have a single acceleration or a horizontal line. And when we have a horizontal line, remember, we're finding the area under our acceleration graph to find velocity. If we have a horizontal line, the integration of this graph, or finding the area, is going to give us a velocity that is linear. And we can check this by taking the slope of our linear velocity graph and seeing that it gives us this horizontal acceleration graph. Another thing is that our velocity is increasing as time goes by. This tells us that our acceleration has to be positive for all times. Next, if we take the area under our velocity graph, we should get a curved or exponential or quadratic looking displacement that's increasing because our velocity is also positive. And also, if we take the slope of every point in our displacement graph, which is taking the derivative, it's going to give us a linear line, and the slope of our displacement graph is velocity. So if we integrated velocity, this would give us the curved displacement. So if a problem tells you that they have a uniform acceleration, the displacement should be curved, and the velocity should be linear, and the acceleration should be horizontal. So from one of these, if they give you either the velocity, if they give you just the acceleration, or just the displacement, you should be able to derive what the velocity and acceleration and displacement is, depending on which one they gave to you. So once again, we can tell that our displacement is going to be exponentially upward because our velocity is positive and increasing, and our acceleration is positive, which tells us that our velocity is linearly increasing. Okay, to wrap up our video, I'm going to be going over a practice problem that utilizes all the skills that we learned today. So part A of question 2. A lab cart moves along a straight horizontal track. The graph describes the relationship between the velocity and the time of the cart. Indicate every time interval for which the speed or magnitude of the velocity of the cart is decreasing. So we know that when the velocity or the magnitude of the speed is decreasing, it should have a negative slope. And we know that a negative slope is a downward rise over a run, or a upward rise and a left run. So here it looks like we're increasing because it's going up, and from 4 to 8 it looks like we're pretty steady. It looks like a zero change in velocity. It looks like a constant 4. Here it looks like our slope is negative, so this looks like it's decreasing. From 10 to 14 it looks steady again at 0 meters per second. And from 14 to 16, it looks like we're decreasing again. So for part A, I would say our time intervals from 8 to 10, we're decreasing. And our time intervals from 14 to 16, we are decreasing our velocity or the magnitude of our speed. Okay, part B is asking, indicate every time at which the cart is at rest. So a lot of common mistakes that students might make is when the velocity is horizontal. That does not mean that our cart is at rest. That rather means it's staying at a constant velocity of 4 meters per second. But let's take a look at times 10 to 14. Our velocity is constant, but it's also at 0 meters per second, indicating that it's at rest. So the times that it's at rest are from 10 seconds to 14 seconds. Part C is asking, determine the horizontal position x of the cart at time 4 seconds if the cart is located at a displacement of 0 when time is 0. So if we know that our initial position, or xi or x naught, is 0 meters, we need to figure out the displacement from 0 to 4 seconds. Remember that this is the velocity versus time graph, and in order to figure out displacement, we need to do the area under the graph from 0 to 4 seconds. So this is a triangle that is 4 by 4, giving us an area of 8. So this tells us that our displacement is 8 meters. Remember that displacement is equal to final position minus initial position. If our displacement is 8 meters, we're looking for our final position, and our initial position is 0, then our final position is going to be 8 meters. Part D is asking, determine the travel distance of the cart over 10 seconds from the beginning. I want you to remember that distance and displacement are not the same. In this case, we can take the area under the graph because the area is all positive. However, if it was asking to find the distance traveled from 0 to 16 seconds, rather than subtracting this area, we would add it to find the distance, and we would subtract it to find displacement. In this case, since it's all positive, we simply just have to find the area under the graph. So I'm going to break this up into 2 small triangles. This is 4 by 4, giving us 8. This is 4 by 4, giving us 16. And this is 2 by 4, giving us 4. And that's going to give us an area of 28, which tells us the distance traveled is 28 meters. Okay, lastly, part G is asking, on the axis below, sketch the acceleration graph for the motion of the cart from 0 seconds to 20 seconds. Okay, so remember what we talked about. The slope of a velocity graph will give us acceleration. And because our velocity graph is once again linear, we don't have to use any calculus or derivatives to figure this out. So let's break this into sections of the linears that stay the same. So 0 to 4, 4 to 8, 8 to 10, 10 to 14, 14 to 16, and then 16 to 20. So it looks like from 0 to 4 seconds, our slope is 4 over 4, which is going to give us 1 meter per second squared. So from 0 to 4 seconds, we're 1 meter per second squared. And then after 4 seconds, we have a slope of 0 from 4 to 8 seconds. So a slope of 0 gives us an acceleration of 0. And then from 8 to 10 seconds, we have a decreasing or negative slope of 2 or 4 over 2, which is going to be 2 meters per second squared. So negative 2 meters per second squared from 8 to 10. Once again, from 10 to 14, we have a slope of 0. This means from 10 to 14 seconds, our acceleration is 0 meters per second squared. And then, small bit here, we have a negative slope of, rise of negative 2 and a run of 2, which is going to give us negative 1 per meters per second squared. So from 14 to 16, we have a negative 1 meters per second squared acceleration. And then once again, from 16 to 20, our slope of our velocity is 0, and that means that our acceleration is 0 meters per second squared from 16 to 20. Okay, so that wraps it up for this video. I hope this video helped, and if you have any more questions on a specific topic, please let me know. Down below in the description, I've linked a practice page for you guys to work on that practices more of the graphs and maybe some additional 2D questions from the previous video. Thank you so much for watching.